Throughout all of history, the night sky has been a source of knowledge and curiosity. The ancient Egyptians believed that the stars existed in both the real world and the afterlife, that the Ba would rise into the night sky and become stars when they died. The Greeks believed that the night sky was a massive, rotating bronze dome, and they used the stars to help develop calendars and keep track of time. Since the early 1600s, the invention of the telescope has captivated minds and spurred all sorts of scientific and philosophical questions. Countless discoveries have been made using these simple devices, and improvements and adjustments to the optics and sensors in them have led to major theories and discoveries about where we are and how we got here. Astronomers have been able to identify and locate the planets, observe nearby galaxies, and estimate the age and origin of our universe. Despite all these advancements, there has always been one drawback all telescopes on Earth have had to deal with: our atmosphere. Although it's great for breathing, our thick atmosphere causes all sorts of problems for incoming light by refracting, reflecting, and absorbing different wavelengths. Think of mirages above pavement on a hot summer day. Shifting air pockets with different temperatures and densities in Earth's atmosphere act as massive lenses, refracting visible light and causing major problems for small light sources such as distant stars. These refractions are what cause the stars to twinkle at night, and in fact those closer to the horizon twinkle more than those directly above us, due to the light having to travel through more atmosphere. Additionally, the water vapor in our lower atmosphere absorbs some of the infrared radiation coming from outer space, and higher up, our ozone absorbs much of the ultraviolet. Even higher in our atmosphere, X-rays and gamma rays are reflected and absorbed, keeping us safe from dangerous cosmic radiation, but limiting what scientists can observe strictly from the ground. Lyman Spitzer, a theoretical physicist and astronomer, proposed a radical new solution to this problem. He proposed that NASA launch a large telescope into space, and along with several other institutions began designing the initial plans for what would be the Hubble Space Telescope. It would have to be able to withstand the freezing temperatures of outer space, as well as the cosmic radiation from the sun and stars, all while being serviceable and repairable by astronauts. This massive engineering project was assigned to Lockheed Missiles, now Lockheed Martin, who designed and tested the machine to match the requirements of NASA. Hubble was designed to be a Cassegrain reflector style of telescope, originally with a primary mirror diameter of 3 meters, or around 10 feet. However, when the budget was estimated to be $500 million, the House Appropriations Subcommittee refused to fund it. In order to cut the budget down to a more feasible $200 million, the mirror would have to be downsized to 2.4 meters. Once the building of the primary mirror was underway by the Perkin-Elmer Corporation, the construction of the housing assembly could begin. Hubble was to be split into 4 major substructures. In the front, a massive aperture door and light shield to allow the telescope to focus on specific light sources while blocking out others. Next, a shell to enclose the assembly mirrors and lenses that gather the light. After that, a section to hold equipment and subsystems for the satellite, such as the onboard computer. And lastly, a massive container to hold the interchangeable scientific instruments and guidance sensors, to which the solar arrays and communication antenna would be attached. Construction of Hubble lasted from 1975 to 1981, and after suffering from several delays due to manufacturing problems, the telescope was finally scheduled for launch in October.
4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission.
Sadly, on January 28th of that year, what would come to be known as the Challenger Space Shuttle disaster occurred, causing all future NASA flights to be grounded indefinitely. This delay caused the cost of the project to skyrocket, as the entire telescope had to be kept in a clean room, purged with nitrogen, for nearly 9 years. Although costing around $6 million per month, this extra time did allow scientists to perform further tests and modifications to the satellite, including swapping out its original failure-prone battery for an improved one. Additionally, the software that was to be used to operate Hubble from the ground was not ready for its original launch date in 1981, so this extra time allowed software engineers to fully design and implement the systems necessary to control Hubble. Finally, on April 24, 1990, the Hubble Space Telescope was launched into outer space, promising to give scientists new insight into all that surrounds us. The original 5 sensors were the Wide Field and Planetary Camera, the Goddard High-Resolution Spectrograph, the High-Speed Photometer, the Faint Object Camera, and the Faint Object Spectrograph. Together, these instruments promised a crystal-clear view into the past and would allow us to see space in detail like never before. Or so we hoped. The first images that came back from Hubble showed signs of a defect in the primary mirror, something called spherical aberration. The flaw was no bigger than 1/50th the thickness of a sheet of paper, caused by a miscalibrated measuring device used to shape the mirror, but was enough to cloud Hubble's vision. The first of many surfacing missions to Hubble was sent to fix this problem, by removing the high-resolution spectrograph and replacing it with CoStar, a corrective optics lens meant to help fix the blurry vision caused by the misshapen mirror. On this mission, the wide field and planetary camera was also upgraded, as well as the solar arrays, gyroscopes, and various fuses. To the applause and relief of astronomers everywhere, the next images Hubble took looked fantastic. Never before was the universe able to be seen in such detail, and in so many different wavelengths of light. Over 10,000 scientific articles have been published based on Hubble data. The telescope helped astronomers narrow down the approximate age of the universe from 10 to 20 billion years down to 13 to 14 billion, and was responsible for the establishment and verification of many scientific theories, such as the existence of gamma-ray bursts and Einstein rings. Hubble was the first to see protoplanetary disks, and was also able to peer into the darkest areas of the night sky to see some of the youngest and most distant galaxies in the universe. Many of the most famous images of distant nebula were taken by Hubble. Although originally planned to be in operation for around 20 years, Hubble is still producing fantastic images 25 years post-launch. Scientists now expect the satellite to last until around 2021 to 2035. Hubble will be succeeded by the James Webb Space Telescope, which has a primary mirror diameter of 6.5 meters, compared to Hubble's 2.4. Despite its plan to launch in October 2018, the James Webb Space Telescope will not entirely replace Hubble, because it is designed to peer into the infrared spectrum of light to see through clouds of gas and into the furthest reaches of our universe. Hubble will hopefully remain in service into the 2030s, advancing our knowledge of the universe for years to come.